Hello there and welcome to another peaceful journey through the wonders of our world. Tonight we drift upward, beyond the familiar ground beneath our feet, beyond the clouds that wrap around mountain peaks, into the vast quiet darkness where Earth meets space. This is a place where silence reigns and beauty unfolds in ways that few human eyes have ever witnessed directly. We are going to explore one of nature's most breathtaking phenomena, the aurora borealis, but not from the ground looking up as most people experience it. Instead, we will see it as astronauts do, floating hundreds of kilometers above our planet, watching these ethereal curtains of light dance across the curve of the Earth below. From this perspective, the northern lights become something entirely different, something almost impossible to describe in ordinary words. If you find these gentle explorations of our world help you unwind at the end of a long day, or if they simply give you a moment of peace in a busy world, feel free to like and subscribe, or share your thoughts in the comments below. It helps others find their way to these quiet moments too, one peaceful soul at a time. But for now, let us begin our ascent into the darkness above, where light and magnetism create one of the most stunning displays in our solar system. The International Space Station orbits Earth at an altitude of roughly 400 kilometers above sea level. At this height, astronauts exist in a realm that is neither fully Earth nor fully space, suspended in a thin atmosphere where the planet's magnetic field still holds sway, but where the vacuum of space begins to assert its presence. It is here, in this liminal zone between worlds, that the aurora takes on its most magnificent form. From the ground, we see the northern lights as shifting curtains hanging in the night sky, green ribbons that seem to flutter like fabric in an invisible wind. But from space, the view transforms completely. The aurora appears as a glowing crown wrapped around the polar regions of our planet, a luminous halo that pulses and shimmers, as if the Earth itself were breathing light into the cosmos. The colors that dance in this celestial display tell stories written in the language of physics and chemistry. The familiar green glow that dominates most aurora displays comes from oxygen atoms roughly 100 kilometers above the Earth's surface. When charged particles from the sun collide with these oxygen atoms, they become excited, absorbing energy before releasing it again as that distinctive emerald light. Higher up, at altitudes of 300 kilometers or more, oxygen produces a deeper red glow, creating layers of color that stack like watercolors bleeding into one another. But the aurora is not limited to oxygen alone. Nitrogen contributes its own palette to this atmospheric art show. At lower altitudes, nitrogen glows with a deep blue or purple hue, while higher up, it shifts to a pink or magenta that seems almost otherworldly. These colors blend and separate, creating combinations that no human artist could ever quite capture. Patterns that exist for mere moments before dissolving into new arrangements. The source of this celestial light show lies 93 million miles away, in the nuclear furnace of our sun. Deep within the solar core, hydrogen atoms fuse together under unimaginable pressure and temperature, releasing energy that eventually makes its way to the sun's surface. But the sun does not simply shine light into space. It also releases a constant stream of charged particles, a solar wind that rushes outward at speeds of several hundred kilometers per second. This solar wind carries with it pieces of the sun itself, protons and electrons that have been stripped from atoms in the star's outer atmosphere. As these particles race through the vacuum of space, they carry magnetic fields with them, creating what scientists call the interplanetary magnetic field. When this solar wind encounters Earth, something remarkable happens. Our planet possesses its own magnetic field, generated by the movement of molten iron in its core. This magnetic field acts like an invisible shield, deflecting most of the solar wind around our planet, like water flowing around a stone in a stream. But the interaction between the solar wind and Earth's magnetic field is not simple. The magnetic fields can connect and disconnect in a process called magnetic reconnection, allowing some of the solar wind's energy to penetrate into Earth's magnetic environment. When this happens, charged particles from the sun become trapped in Earth's magnetic field lines, spiraling along these invisible pathways toward the polar regions. As they descend deeper into our atmosphere, they begin to collide with the gases that surround our planet. Each collision transfers energy, and when atoms release this energy, they emit light. The result is the aurora, a visible manifestation of the invisible forces that constantly surround our world. From the International Space Station, astronauts can watch this process unfold in real time. They see the solar wind as it interacts with Earth's magnetic field, creating disturbances that ripple through the upper atmosphere. They witness the moment when charged particles penetrate the magnetic shield and begin their spiral descent toward the poles. And they watch as the aurora blooms into existence, sheets of light that seem to emerge from nowhere and spread across hundreds of kilometers in minutes. The shape and intensity of the aurora depend on conditions both in space and in Earth's upper atmosphere. During periods of high solar activity, when the sun releases particularly energetic bursts of particles in events called solar storms, the aurora can become dramatically more intense and widespread. These storms can push the aurora much farther from the poles than usual, sometimes making the northern lights visible as far south as the northern United States or southern Europe. But even during quiet periods, the aurora maintains a constant presence around the polar regions. From space, astronauts can see this auroral oval, a ring of faint light that encircles each magnetic pole. The oval expands and contracts based on the strength of the solar wind, sometimes shrinking to a tight band around the pole, other times expanding to cover vast areas of the polar regions. The motion of the aurora as seen from space reveals the dynamic nature of Earth's magnetic environment. The lights pulse and flicker as magnetic field lines reconnect and snap like rubber bands. Waves of light roll across the polar regions as disturbances in the solar wind wash over Earth's magnetic field. Sometimes the aurora forms distinct arcs that stretch from horizon to horizon, while other times it appears as scattered patches that dance independently across the darkness. One of the most striking aspects of viewing the aurora from space is the sense of scale it provides. From the ground, the northern lights can seem to fill the entire sky, creating an immersive experience that surrounds the observer. But from orbit, the aurora reveals itself as just one part of a much larger system. Astronauts can see how the lights connect the polar regions, forming a bridge of luminescence that spans the gap between day and night on Earth's surface. During the polar winter, when the northern regions of Earth are tilted away from the sun and shrouded in months of darkness, the aurora becomes the primary source of light for vast areas of the planet. From space, these regions glow with an ethereal radiance that seems to pulse with the rhythm of some cosmic heartbeat. The lights reflect off ice and snow, creating a feedback loop that amplifies the aurora's glow and makes the polar landscape shimmer like a jewel in the darkness. The aurora also interacts with other phenomena in Earth's upper atmosphere, creating complex displays that can only be fully appreciated from space. Sometimes the lights appear to dance with noctilucent clouds, high-altitude ice crystal formations that glow with a silvery blue light. Other times, the aurora seems to compete with lightning from thunderstorms far below, creating a layered light show that spans multiple levels of the atmosphere. Astronauts who have witnessed the aurora from space often describe it as a transcendent experience, something that fundamentally changes their understanding of Earth's place in the solar system. They speak of watching the lights emerge from the darkness like a slow sunrise, building in intensity until the entire polar region glows with an inner fire. They describe the colors as more vivid and varied than anything visible from the ground, with subtle hues and gradations that cameras struggle to capture. The silence of space adds another dimension to the experience. Unlike viewers on the ground, who might hear the wind or feel the cold night air, astronauts watch the aurora unfold in perfect quiet. There is no sound in the vacuum of space, so the lights dance in absolute silence, their movements seeming even more graceful and mysterious without any accompanying audio. This silence allows observers to focus entirely on the visual spectacle, to lose themselves in the flowing patterns of light without distraction. From this orbital perspective, the aurora reveals connections that are invisible from the ground. Astronauts can see how the lights in the northern hemisphere mirror those in the southern hemisphere, both driven by the same solar-wind interactions, but separated by the bulk of the planet. They can watch as disturbances in one auroral oval propagate to the other, demonstrating the global nature of Earth's magnetic field. The International Space Station's orbit carries it through different parts of Earth's magnetic environment, providing astronauts with varying perspectives on the aurora throughout their journey around the planet. Sometimes the station passes directly beneath the auroral oval, giving crew members a close-up view of the lights from below. Other times, the orbit carries them to the side of the aurora, allowing them to see the three-dimensional structure of the light curtains as they extend upward into space. The varying altitudes at which the aurora occurs create a layered effect that becomes particularly apparent from the unique vantage point of space. The lowest auroral emissions occur at around 80 kilometers above Earth's surface, while the highest can extend upward to over 1,000 kilometers. From the International Space Station, positioned in the middle of this range, astronauts can observe both the lower curtains of light beneath them and the fainter upper reaches that stretch toward the stars. This vertical structure of the aurora creates depth and dimension that ground-based observers rarely perceive. The lights appear to have substance and volume, like luminous fog banks suspended in the thin upper atmosphere. As the charged particles from the solar wind spiral along Earth's magnetic field lines, they create these towering columns of light that can extend hundreds of kilometers into space. The result is a three-dimensional light sculpture that shifts and evolves with each passing moment. The speed at which auroral displays can change often surprises even seasoned space travelers. What begins as a faint glow on the horizon can explode into a brilliant cascade of light within minutes. Conversely, intense displays can fade to barely perceptible wisps just as quickly. This rapid transformation occurs because the aurora responds directly to changes in the solar wind and Earth's magnetic field, both of which can fluctuate on timescales of minutes or even seconds. During particularly active periods, the aurora can pulse with a rhythm that seems almost alive. These pulsations occur when waves in Earth's magnetic field cause the charged particle precipitation to vary in intensity. From space, these rhythmic brightenings create the impression of a vast organism breathing light into the cosmos. The pulsations can be synchronized across hundreds of kilometers, suggesting that large-scale processes in Earth's magnetic environment are orchestrating the display. The interaction between the aurora and the underlying planet creates visual effects that are only visible from orbit. The lights reflect off clouds, ice sheets, and snow-covered landscapes, creating secondary illumination that can make entire continents glow with a soft radiance. This reflected auroral light is particularly striking over the Arctic Ocean, where the aurora bounces off sea ice to create an ethereal glow that extends far beyond the direct footprint of the lights themselves. Astronauts also witness phenomena that have no equivalent in ground-based aurora observations. Sometimes they see the aurora interacting with the thin atmosphere at their orbital altitude, creating a faint glow around the space station itself. This interaction occurs when the station passes through regions where auroral particles are present, causing the spacecraft's surface to fluoresce faintly. The effect is subtle but unmistakable, a reminder that the aurora is not just a distant light show, but an active process occurring in the same environment where the astronauts live and work. The curvature of Earth adds another dimension to the space-based aurora experience. From the ground, the horizon limits our view and creates the impression that the aurora is a local phenomenon occurring directly overhead. From space, however, the aurora reveals itself as a planetary scale process. Astronauts can see the lights wrapping around Earth's curvature, extending beyond the horizon in all directions. This perspective emphasizes the global nature of the aurora and its connection to Earth's magnetic field, which itself encircles the entire planet. Different seasons bring distinct characteristics to the space-based aurora viewing experience. During the equinoxes in spring and fall, when Earth's magnetic field is optimally aligned with the solar wind, auroral activity tends to be at its most intense. From space, these seasonal peaks create spectacular displays that can last for hours and cover vast areas of the polar regions. The lights during these periods often show more complex structure and more rapid movement, reflecting the enhanced energy input from the solar wind. The summer and winter solstices bring their own unique auroral characteristics as viewed from space. During the Northern Hemisphere's summer solstice, when the North Pole is tilted toward the sun, the aurora occurs in continuous daylight. From space, astronauts can see the faint auroral glow competing with sunlight, creating a subtle display that would be completely invisible from the ground. This daylight aurora appears as pale wisps of light that seem to shimmer just above the bright polar landscape. Conversely, during the winter solstice, when the polar regions are shrouded in continuous darkness, the aurora becomes the dominant source of illumination across vast areas of the planet. From space, these winter displays appear more vivid and dramatic against the dark polar landscape. The contrast between the glowing aurora and the dark Earth below creates some of the most photogenic conditions for space-based aurora observation. The aurora's relationship with Earth's rotation creates patterns that unfold over the course of each orbital period. As the International Space Station completes its 90-minute journey around the planet, the aurora appears to shift and change position. This apparent motion results from the combination of the station's orbital movement and the aurora's tendency to remain fixed relative to Earth's magnetic field rather than its geographic coordinates. Temperature variations in Earth's upper atmosphere also influence the appearance of the aurora as seen from space. During periods of high solar activity, the upper atmosphere heats up and expands, changing the density of gases at auroral altitudes. This expansion affects the colors and intensity of the aurora, sometimes shifting the dominant emission from green to red as the altitude of peak particle interaction rises into regions where oxygen produces red rather than green light. The magnetic field lines that guide auroral particles create invisible highways in space that astronauts can sometimes infer from the patterns of the lights below. When the aurora forms distinct arcs or rays, these features often align with the direction of the local magnetic field. From space, these alignments become more apparent, revealing the underlying magnetic structure that shapes the auroral display. The result is a visual representation of invisible forces, a way to see the magnetic field lines that surround our planet. Solar wind variations create different types of auroral displays that are particularly evident from the space-based perspective. During steady solar wind conditions, the aurora tends to form relatively stable arcs and bands that can persist for hours. But when the solar wind becomes turbulent, or when solar storms impact Earth's magnetic field, the aurora transforms into rapidly changing curtains and spirals that dance across the polar regions with remarkable speed and complexity. The phenomenon, known as substorms, creates some of the most dramatic auroral displays visible from space. These events occur when energy stored in Earth's magnetic tail is suddenly released, causing the aurora to brighten explosively and expand rapidly toward the equator. From orbit, astronauts can watch these substorms develop in real time, seeing the initial brightening followed by the rapid expansion of the auroral oval. The entire sequence can unfold in less than an hour, transforming a quiet auroral display into a brilliant spectacle that can be seen across multiple time zones. High-speed cameras aboard the International Space Station have revealed details of auroral motion that were previously unknown. The lights move in complex patterns that include waves, spirals, and flickering structures that change on timescales of seconds. These rapid motions reflect the dynamic nature of the particle precipitation processes that create the aurora, showing how quickly conditions can change in Earth's upper atmosphere. The aurora's interaction with Earth's atmosphere creates effects that extend far beyond the visible light display. The same processes that produce the beautiful lights also generate radio waves, heat the upper atmosphere, and create electrical currents that flow through the polar regions. From space, astronauts are positioned to observe not just the optical aurora, but also these related phenomena that help scientists understand the complex physics of Earth's magnetic environment. As our journey continues through this celestial light show, we begin to appreciate how the aurora serves as a window into the fundamental processes that shape our planet's relationship with the sun. The dancing lights reveal the constant interaction between solar and terrestrial forces, a cosmic dance that has been ongoing for billions of years and will continue long after our brief human presence has faded from memory. Presence has faded from memory. The aurora's influence extends beyond the mesmerizing visual display, creating ripple effects throughout Earth's entire atmospheric system. From the International Space Station's privileged vantage point, astronauts can observe how the energetic particles that create the northern lights also generate heat in the upper atmosphere. This heating causes the thin air at orbital altitudes to expand, creating what scientists call atmospheric drag that can actually affect the station's orbit over time. During particularly intense auroral displays, this heating becomes so pronounced that satellites in low Earth orbit experience increased atmospheric resistance. The aurora essentially puffs up the atmosphere, reaching higher into space and creating more friction for orbiting objects. Astronauts have reported feeling subtle vibrations in the station during the most powerful geomagnetic storms, a tangible reminder that they are witnessing forces capable of moving entire layers of our planet's atmosphere. The electromagnetic nature of the aurora creates another fascinating phenomenon visible from space. The same charged particles that produce the lights also generate powerful radio emissions that can interfere with communication systems. From orbit, astronauts sometimes experience radio blackouts during intense auroral displays, finding themselves temporarily cut off from ground control as the dancing lights below disrupt radio waves across entire continents. These radio effects reveal the aurora's three-dimensional structure in ways that optical observations alone cannot capture. Radio telescopes on the ground can map the regions where auroral particles are most concentrated, creating invisible sculptures in space that astronauts can correlate with the visible light patterns below them. The result is a more complete understanding of how the aurora extends both upward into space and downward into Earth's atmosphere. The seasonal variations in Earth's magnetic field orientation create distinct patterns in the aurora that become particularly apparent from the space-based perspective. During the spring equinox, when Earth's magnetic field is tilted optimally relative to the solar wind, the aurora tends to form more symmetric patterns around both poles. From space, these symmetric displays create a striking visual balance, with the northern and southern auroral ovals appearing as mirror images of each other across the bulk of the planet. As the seasons progress towards summer and winter, this symmetry gradually breaks down due to the changing angle between Earth's magnetic field and the incoming solar wind. The aurora in one hemisphere may become more intense while the other fades, creating an asymmetric display that reflects the complex geometry of magnetic field interactions. Astronauts who spend extended periods on the International Space Station become familiar with these seasonal patterns, learning to predict the characteristics of auroral displays based on the time of year. The connection between the aurora and Earth's weather systems creates subtle interactions that are only beginning to be understood. Some research suggests that intense auroral activity can influence atmospheric circulation patterns in ways that eventually affect weather at ground level. From space, astronauts can observe both the aurora and large-scale weather patterns simultaneously, providing a unique perspective on these potential connections. During winter months in the polar regions, the aurora often appears to interact with polar stratospheric clouds, high-altitude ice crystal formations that create their own ethereal glow. From the International Space Station, these interactions create layered displays of light that span multiple levels of the atmosphere. The aurora dances above while the stratospheric clouds shimmer below, creating a three-dimensional light show that extends from near the Earth's surface up to the edge of space. The timing of auroral displays follows patterns that reflect the sun's rotation and the structure of the solar wind. The sun rotates once every 27 days, and features on its surface like coronal holes and active regions can create streams of fast-moving solar wind that sweep past Earth at regular intervals. From space, astronauts can sometimes observe the aurora intensifying with this 27-day rhythm, a visible reminder of our planet's connection to the rotating sun. Solar storms create the most spectacular auroral displays visible from space, but they also pose challenges for astronauts living and working in orbit. During major geomagnetic events, the radiation environment around Earth becomes more hazardous, and crew members may need to shelter in the most shielded parts of the station. These periods of heightened radiation often coincide with the most brilliant auroral displays, creating a bittersweet situation where the most beautiful light shows are also the most dangerous. The aurora's response to different types of solar wind reveals the sophisticated nature of Earth's magnetic field system. When the solar wind carries magnetic fields that are aligned opposite to Earth's field, magnetic reconnection occurs more readily, leading to enhanced auroral activity. From space, astronauts can observe how the aurora brightens and expands during these periods of optimal magnetic coupling between the Sun and Earth. Conversely, when the solar wind's magnetic field is aligned parallel to Earth's field, auroral activity tends to remain subdued. These quiet periods allow astronauts to observe the more subtle aspects of the aurora, including the faint background glow that persists even during magnetically quiet conditions. This persistent aurora reveals that some level of solar wind interaction occurs constantly, maintaining a baseline level of particle precipitation that creates a permanent, if faint, auroral presence. The altitude structure of the aurora creates optical effects that are particularly striking from the space-based perspective. Different gases in Earth's atmosphere emit light at different altitudes when struck by auroral particles. Oxygen dominates at higher altitudes, producing red light, while nitrogen becomes more prominent lower down, contributing blue and purple hues. From the International Space Station, positioned in the middle of this altitude range, astronauts can see both the red oxygen emissions above them and the blue nitrogen emissions below. This layered structure creates depth in the auroral display that ground-based observers rarely perceive. The aurora appears to have volume and substance, like luminous fog banks suspended in the thin upper atmosphere. As particles spiral along magnetic field lines, they create these towering columns of light that can extend hundreds of kilometers, both above and below the station's orbit. The motion of the aurora reveals the dynamic nature of magnetic field line geometry around Earth. Field lines near the poles are nearly vertical, creating curtain-like aurora that appear to hang straight down from space. But as the field lines curve away from the poles, they create more horizontal auroral structures that stretch across the sky like ribbons. From orbit, astronauts can see this entire range of orientations simultaneously, revealing the three-dimensional structure of Earth's magnetic field. Substorms in the aurora create some of the most dramatic displays visible from space. These events begin with a sudden brightening of the aurora, followed by rapid expansion and complex motion patterns. From the International Space Station, astronauts can watch these substorms develop in real time, seeing the initial trigger followed by waves of light that propagate across hundreds of kilometers within minutes. The entire sequence unfolds like a slow-motion explosion of light across the polar landscape. The interaction between the aurora and the thin atmosphere at the station's altitude creates phenomena that have no equivalent in ground-based observations. Sometimes the station itself becomes surrounded by a faint auroral glow as it passes through regions of enhanced particle precipitation. This interaction between the spacecraft and the auroral environment creates a subtle but unmistakable luminescence around the station's structure. Variations in solar wind density create pulsing patterns in the aurora that are particularly evident from the space-based perspective. As denser and less dense regions of the solar wind sweep past Earth, The aurora brightens and dims in response. These variations can create rhythmic pulsing that spans the entire auroral oval, suggesting large-scale organization in both the solar wind and Earth's magnetic response. The aurora's connection to Earth's internal magnetic field creates patterns that reflect the planet's deep interior structure. Variations in magnetic field strength caused by geological features can influence where and how intensely the aurora appears. From space, these magnetic anomalies create subtle but persistent variations in auroral patterns that help scientists understand Earth's internal structure. During periods of very high solar activity, the aurora can expand far beyond its normal boundaries, sometimes reaching middle latitudes where it would normally never appear. From orbit, astronauts can observe these expansions in real time, watching as the auroral oval grows to encompass regions normally too far from the magnetic poles to experience auroral activity. These expanded displays can cover areas larger than entire continents, creating a planetary-scale light show. The aurora's interaction with Earth's rotation creates patterns that unfold over multiple timescales. The daily rotation creates apparent motion in the auroral display as the station orbits through different local times. But longer-term variations related to seasonal changes and solar cycle effects create patterns that can only be appreciated over months or years of observation. High-resolution cameras aboard the International Space Station have revealed fine-scale structures in the aurora that were previously unknown. Individual rays and spirals can be resolved, showing motion patterns that change on timescales of seconds. These rapid variations reflect the turbulent nature of the particle precipitation processes, revealing a level of complexity that requires the unique perspective of space-based observation to fully appreciate. The electromagnetic environment created by the aurora generates effects that extend throughout the space around Earth. Radio waves produced by the auroral processes can be detected by sensitive instruments, creating an acoustic signature of the light display. From orbit, astronauts are positioned within this electromagnetic environment, experiencing directly the forces that create the beautiful lights below. As we continue our quiet journey through this celestial theater, the aurora reveals itself as far more than just a pretty light show. It becomes a visible manifestation of the invisible forces that constantly shape our planet's relationship with the sun, a reminder that Earth exists within a dynamic and ever-changing cosmic environment. The dancing lights serve as a bridge between the terrestrial and the celestial, connecting the solid ground beneath our feet to the vast energies that flow throughout our solar system. Our solar system. The aurora's influence on Earth's magnetic field creates feedback loops that astronauts can observe unfolding in real time from their orbital perch. When particularly intense displays occur, the aurora doesn't simply respond to magnetic field changes, it actively modifies the field itself. The electrical currents flowing through the upper atmosphere during major auroral events can temporarily reshape the magnetic field lines, creating new pathways for charged particles and altering the very structure that guides the light display. From the International Space Station, these feedback effects become visible as sudden changes in auroral patterns that seem to have no direct relationship to solar wind variations. The aurora appears to develop a life of its own during these moments, creating new structures and motion patterns that emerge from within the system rather than being imposed from outside. These self-organizing behaviors reveal the aurora as a complex, adaptive system, one that can respond to and modify its own environment. The temperature variations created by auroral heating have cascading effects throughout Earth's atmospheric layers. The energy deposited by auroral particles doesn't simply heat the immediate region where the lights appear. It sets up circulation patterns that can influence atmospheric dynamics hundreds of kilometers away. From space, astronauts can sometimes observe these thermal effects as subtle changes in cloud patterns or atmospheric density variations that correlate with auroral activity. During the most intense geomagnetic storms, the aurora can actually help protect Earth's surface from harmful radiation. The same processes that create the brilliant light displays also accelerate charged particles away from the planet, creating a natural particle accelerator that helps clear dangerous radiation from near-Earth space. From orbit, astronauts witness this protective effect as the aurora brightens dramatically, while radiation levels in their immediate environment actually decrease. The aurora's connection to Earth's rotation creates tidal effects in the upper atmosphere that become apparent from the space-based perspective. Just as the moon creates tides in Earth's oceans, the rotating magnetic field creates subtle tides in the charged particle populations that fuel the aurora. These magnetic tides cause the aurora to pulse with periods related to Earth's rotation, creating rhythmic variations that can be observed over the course of multiple orbital passes. The seasonal tilt of Earth's axis affects not just the intensity of auroral displays, but also their fundamental character. During winter in the northern hemisphere, when the North Pole is tilted away from the sun, the magnetic field lines on the night side of Earth become stretched into long tails that extend far into space. From the International Space Station, astronauts can observe how this seasonal stretching changes the shape and behavior of the auroral oval, creating displays that are fundamentally different from those occurring during other times of the year. The aurora's interaction with the solar wind creates standing wave patterns that extend throughout Earth's magnetosphere. These waves, invisible except for their effects on the aurora, can be observed from space as regular pulsations and oscillations in the light display. The waves propagate along magnetic field lines like vibrations on a guitar string, creating harmonics and resonances that give the aurora its characteristic rhythmic behaviors. Spacecraft flying through the auroral regions have detected acoustic waves generated by the same processes that create the lights. These sounds, though inaudible in the vacuum of space, can be converted to audio frequencies that reveal the aurora's hidden acoustic signature. From the station, astronauts are positioned within this acoustic environment, experiencing the aurora not just as a visual phenomenon, but as part of a complex symphony of electromagnetic waves and particle interactions. The aurora's role in Earth's energy budget becomes apparent from the space-based perspective. The lights represent a visible release of energy that has been stored in Earth's magnetic field, sometimes for hours or days before being suddenly discharged in brilliant displays. From orbit, astronauts can observe this energy storage and release cycle as the aurora builds gradually during quiet periods and then explodes into activity during substorms. The interaction between multiple auroral arcs creates interference patterns that are particularly striking when viewed from space. When several parallel arcs of aurora appear simultaneously, they can create beat patterns and standing waves that march across the polar landscape like ripples on a pond. These interference effects reveal the wave-like nature of the auroral processes and demonstrate how individual structures can interact to create more complex displays. The aurora's response to variations in Earth's magnetic field strength creates regional differences in display characteristics that are most apparent from the orbital perspective. Areas where the magnetic field is stronger tend to channel auroral particles more efficiently, creating brighter and more concentrated displays. Conversely, regions where the field is weaker often show more diffuse and scattered auroral activity. From space, these variations create a map of Earth's magnetic field strength written in light across the polar landscape. The connection between the aurora and Earth's internal heat sources creates subtle but persistent patterns that can only be appreciated from long-term space-based observations. Regions where geothermal activity brings additional heat to the upper atmosphere tend to show enhanced auroral activity, creating hotspots of light that persist across multiple geomagnetic events. These thermal effects link the aurora to processes occurring deep within Earth's interior, connecting the light display to the planet's geological activity. During solar minimum periods, when solar activity is at its lowest, the aurora reveals its most subtle and delicate structures. Without the overwhelming influence of strong solar storms, the quiet auroral processes become visible from space, as faint but persistent glows that follow the exact contours of Earth's magnetic field. These quiet displays often show more organized and predictable patterns, revealing the underlying geometry of the magnetic system without the chaotic disruptions of active periods. The aurora's influence on atmospheric chemistry creates effects that extend far beyond the immediate light-producing regions. The energetic particles that create the displays also break apart molecules in the upper atmosphere, creating new chemical compounds that can affect ozone concentrations and atmospheric composition. From space, these chemical effects are invisible to the eye, but create measurable changes in atmospheric properties that influence everything from radio propagation to climate patterns. The three-dimensional structure of the aurora creates shadows and illumination patterns on Earth's surface that are only visible from orbit. During bright displays, the aurora can actually cast shadows on the snow-covered polar landscape below, creating a secondary light show of shifting shadows and reflected auroral light. These ground-level effects, invisible to surface observers who are surrounded by the light, become apparent from the elevated perspective of space. The aurora's magnetic field interactions create electric fields that extend throughout the polar regions, influencing everything from radio communications to power grid stability on the ground. From the International Space Station, these electric field effects can be inferred from the motion patterns of the aurora itself, which often flow along electric field lines like luminous rivers following invisible channels in the upper atmosphere. The seasonal variations in atmospheric composition affect the colors and intensity of auroral displays in ways that are most apparent from the space-based perspective. During spring and fall, when atmospheric mixing is most active, the aurora often shows more varied colors and more complex vertical structure. Summer and winter displays tend to be more uniform in color, but can show greater horizontal extent, as the seasonal atmospheric conditions allow auroral particles to penetrate to different altitudes. The aurora's connection to the 11-year solar cycle creates long-term patterns that can only be appreciated through extended space-based observations. During solar maximum periods, the aurora tends to be more chaotic and unpredictable, with frequent substorms and rapid changes in intensity. Solar minimum displays are often more organized and persistent, showing clear relationships to the underlying magnetic field structure that becomes obscured during more active periods. The interaction between the aurora and Earth's bow shock, the boundary where the solar wind first encounters Earth's magnetic field, creates precursor effects that can be observed from space as subtle changes in auroral activity. These precursor signals often appear as faint brightenings or changes in auroral motion that occur minutes before the main solar wind disturbance reaches the aurora itself, providing early warning of impending magnetic storms. The aurora's role in coupling different regions of Earth's atmosphere creates vertical transport effects that move energy and materials between atmospheric layers. From orbit, these coupling effects can be inferred from changes in auroral altitude and intensity that reflect the varying efficiency of particle precipitation at different atmospheric levels. The aurora acts as a conduit connecting the space environment to the lower atmosphere, facilitating exchanges that would otherwise be impossible. The electromagnetic radiation generated by auroral processes creates a complex spectrum of emissions that extends far beyond visible light. Radio waves, X-rays, and ultraviolet radiation all accompany the visible aurora, creating a multispectral display that reveals different aspects of the underlying physics. From the International Space Station, instruments can detect this full spectrum of emissions, providing a more complete picture of the auroral phenomenon than is possible from ground-based observations. The aurora's interaction with the thin atmospheric gases at orbital altitudes creates phenomena that blur the boundary between Earth's atmosphere and space. Molecules excited by auroral processes can be ejected from the atmosphere entirely, contributing to atmospheric loss processes that slowly change Earth's atmospheric composition over geological timescales. From space, these escape processes are visible as faint extensions of the aurora that reach upward toward the stars. The rhythmic pulsations that characterize many auroral displays reflect resonances in Earth's magnetic field system that act like a vast musical instrument. Different magnetic field lines have different natural frequencies, creating harmonics and overtones that give the aurora its characteristic temporal structure. From orbit, these musical properties of the magnetosphere become visible as coordinated pulsations that can span entire hemispheres. The aurora's response to the structure of the solar wind reveals details about conditions millions of kilometers away in space. Variations in solar wind density, speed, and magnetic field orientation all leave their signatures in the auroral display, creating a visual record of space weather conditions throughout the inner solar system. From the International Space Station, astronauts become witnesses to cosmic events occurring on scales vastly larger than Earth itself. As our journey through this luminous realm continues, we begin to understand that the aurora serves as Earth's signature in space, a unique fingerprint that reveals the planet's magnetic personality to the cosmos. No two planets have identical magnetic fields, and thus no two worlds would produce exactly the same auroral displays. The northern lights become not just a beautiful phenomenon, but a fundamental expression of what makes Earth unique among all the worlds we know. The aurora's persistence through billions of years of Earth's history connects us to the deep past and far future of our planet. The same magnetic field processes that create today's displays have been operating since Earth first developed its magnetic shield, protecting the planet's atmosphere and creating these celestial light shows for eons before any eyes existed to witness them. From space, we glimpse not just a momentary display, but a window into the fundamental forces that have shaped our world since its earliest days. The aurora's relationship with Earth's magnetic field reveals patterns that extend far beyond our planet's immediate vicinity. From the International Space Station, astronauts can observe how the lights respond to magnetic field lines that stretch hundreds of thousands of kilometers into space, connecting Earth to regions where the solar wind first encounters our planetary magnetic shield. These extended field lines act like cosmic highways, guiding charged particles from the distant reaches of space down into our upper atmosphere, where they create the luminous displays below. During periods of magnetic reconnection, when Earth's field lines temporarily merge with those carried by the solar wind, the aurora undergoes dramatic transformations that unfold like slow-motion fireworks across the polar regions. From orbit, these reconnection events appear as sudden brightenings, followed by explosive expansions of the auroral oval. The lights seem to reach outward from their normal boundaries, stretching toward lower latitudes, as if the aurora itself were trying to embrace more of the planet. The varying density of Earth's upper atmosphere creates layers within the auroral display that become particularly apparent from the space-based perspective. During solar maximum periods, when increased solar radiation heats and expands the upper atmosphere, the aurora tends to occur at higher altitudes, where the thinner air allows particles to penetrate deeper before colliding with atmospheric gases. Conversely, during solar minimum, the contracted atmosphere creates more concentrated auroral displays at lower altitudes, producing brighter and more defined light curtains. The aurora's interaction with atmospheric tides creates subtle but persistent variations that follow the rhythm of Earth's rotation and orbital motion. These atmospheric tides, driven by solar heating and gravitational forces, cause regular changes in upper atmospheric density that influence how and where auroral particles deposit their energy. From the International Space Station, these tidal effects appear as gradual shifts in auroral intensity and altitude that cycle with periods ranging from hours to days. The electromagnetic environment surrounding Earth during auroral displays creates radio signatures that extend throughout the magnetosphere. These radio emissions, generated by the same particle acceleration processes that produce the visible lights, can be detected by sensitive instruments as far away as the outer planets. From orbit, astronauts exist within this radio environment, surrounded by electromagnetic waves that carry information about auroral processes occurring thousands of kilometers away. The aurora's response to seasonal changes in Earth's magnetic field orientation creates annual patterns that reflect our planet's journey around the Sun. As Earth orbits the Sun, The angle between our magnetic field and the incoming solar wind changes continuously, creating seasonal variations in magnetic reconnection efficiency. From space, these seasonal effects appear as gradual changes in auroral character, with spring and fall displays often showing more symmetric patterns, while summer and winter auroras can be more asymmetric and variable. The interaction between different types of solar wind creates distinct auroral signatures that are most apparent from the orbital perspective. Fast solar wind streams, often originating from coronal holes on the Sun, create persistent but relatively gentle auroral displays, characterized by smooth, flowing motions and gradual intensity changes. In contrast, solar wind, associated with coronal mass ejections, produces more chaotic and rapidly changing displays, with sudden brightenings and complex motion patterns that can span entire continents. The aurora's three-dimensional structure creates optical illusions that can only be resolved from the space-based viewpoint. What appears from the ground as a single curtain of light often reveals itself from orbit as multiple parallel sheets separated by tens of kilometers. These multiple layers create depth and complexity in the display that ground-based observers cannot perceive, revealing the aurora as a truly three-dimensional phenomenon rather than a simple overhead canopy. The temperature gradients created by auroral heating generate atmospheric waves that propagate far beyond the immediate auroral zone. These waves, similar to the ripples created by dropping a stone in still water, carry energy and momentum throughout the upper atmosphere, influencing weather patterns and atmospheric circulation on a global scale. From the International Space Station, these wave effects can sometimes be inferred from subtle changes in atmospheric density and auroral morphology. The aurora's magnetic field interactions create current systems that flow through both the upper atmosphere and the space surrounding Earth. These auroral electrojets, as scientists call them, can carry millions of amperes of electrical current across the polar regions. From orbit, the effects of these current systems become visible as organized flow patterns in the aurora itself, with the lights following the paths of electrical current, like luminous rivers flowing through the upper atmosphere. The solar wind's magnetic field orientation plays a crucial role in determining the intensity and location of auroral displays. When the solar wind carries magnetic fields that are oriented southward, opposite to Earth's northward pointing field at the magnetic poles, conditions become optimal for magnetic reconnection and enhanced auroral activity. From space, astronauts can observe how the aurora responds to these changing magnetic conditions, brightening and expanding when reconnection is efficient and dimming when the magnetic fields are poorly coupled. The aurora's interaction with Earth's plasmasphere, a region of dense cold plasma surrounding our planet, creates boundaries and transitions that are visible from orbit as sharp edges in the auroral display. These boundaries mark the transition between different regions of Earth's magnetic environment, each with its own characteristic particle populations and magnetic field properties. From the International Space Station, these plasma boundaries appear as distinct features in the aurora that remain relatively stable even as the overall display evolves and changes. The connection between the aurora and Earth's ring current, a belt of energetic particles that circles the planet during magnetic storms, creates feedback loops that influence both phenomena simultaneously. As the ring current intensifies during magnetic storms, it modifies Earth's magnetic field in ways that affect auroral particle precipitation. From orbit, these interactions appear as changes in auroral intensity and location that correlate with the development and decay of magnetic storm conditions. The aurora's role in atmospheric escape processes becomes apparent from the space-based perspective during periods of intense activity. The same energetic processes that create the brilliant light displays also accelerate atmospheric particles to escape velocities, contributing to the slow loss of Earth's atmosphere to space. From the International Space Station, these escape processes are visible as faint extensions of the aurora that reach upward into the space environment, marking the boundary where Earth's atmosphere gradually merges with the vacuum of space. The diurnal variations in auroral activity reflect the changing geometry between Earth's magnetic field and the solar wind as our planet rotates. Different local times experience different magnetic field configurations, leading to systematic variations in auroral intensity and morphology throughout the day. From orbit, these diurnal patterns become apparent as regular changes in the aurora that cycle with Earth's rotation period. The aurora's interaction with satellite orbits creates practical effects that astronauts can observe directly. During intense auroral displays, the heating of the upper atmosphere increases atmospheric drag on low Earth orbit satellites, causing their orbits to decay more rapidly. From the International Space Station, these effects can sometimes be felt as subtle changes in orbital dynamics, a tangible reminder that the beautiful light display below has real consequences for space operations. The connection between the aurora and Earth's bow shock creates precursor effects that can be observed from space as subtle changes in auroral activity minutes before major magnetic disturbances arrive. These precursor signals propagate along magnetic field lines at speeds much faster than the solar wind itself, providing early warning of impending geomagnetic activity. From orbit, these precursors appear as faint brightenings or motion changes in the aurora that herald more dramatic displays to come. The aurora's response to the solar rotation period creates 27-day cycles in activity that reflect the structure of the solar wind as it streams past Earth. Coronal holes and active regions on the sun's surface create fast and slow solar wind streams that sweep past our planet with each solar rotation. From the International Space Station, these solar rotation effects appear as recurring patterns in auroral activity that can be predicted based on solar observations made weeks in advance. The interaction between the aurora and Earth's neutral atmosphere creates chemical reactions that produce new atmospheric constituents, with lifetimes ranging from minutes to months. These auroral chemistry effects can influence atmospheric composition over large regions, creating changes that persist long after the auroral display itself has faded. From orbit, these chemical effects are invisible to direct observation, but create measurable changes in atmospheric properties that influence radio propagation and other space weather phenomena. The aurora's three-dimensional current systems create magnetic field perturbations that extend throughout near-Earth space. These current-induced magnetic fields can be detected by sensitive magnetometers on satellites and space stations, creating a magnetic signature of the auroral display that complements the visual observations. From the International Space Station, these magnetic effects provide additional information about auroral processes that cannot be obtained from optical observations alone. The seasonal variations in atmospheric composition affect the efficiency of auroral particle precipitation in ways that create systematic differences between displays occurring at different times of year. Winter displays often penetrate to lower altitudes due to the denser atmospheric conditions, while summer auroras may remain at higher altitudes, where the expanded atmosphere provides different interaction conditions. From space, these seasonal effects appear as systematic changes in auroral altitude and intensity that correlate with atmospheric seasonal cycles. The aurora's connection to Earth's radiation belts creates interactions between trapped and precipitating particle populations that influence both phenomena simultaneously. During magnetic storms, particles can be transferred between the radiation belts and the auroral precipitation regions, creating complex dynamics that affect both the aurora and the space radiation environment. From orbit, these interactions appear as changes in auroral morphology that correlate with radiation belt activity. The electromagnetic waves generated by auroral processes create a complex spectrum of emissions that extends from extremely low frequencies to optical wavelengths and beyond. This broad-spectrum electromagnetic signature provides information about different aspects of the auroral phenomenon, from the large-scale current systems to the microscale particle acceleration processes. From the International Space Station, instruments can detect portions of this electromagnetic spectrum, providing a multi-wavelength view of auroral processes. The aurora's role in coupling the solar wind energy to Earth's upper atmosphere makes it a crucial component of the global energy budget during magnetic storms. The energy deposited by auroral processes can exceed the total global electrical power consumption during major geomagnetic events, demonstrating the enormous scales of energy involved in space weather phenomena. From orbit, this energy deposition appears as the brilliant light displays that can illuminate entire continents with their ethereal glow. The interaction between the aurora and the interplanetary magnetic field creates conditions that can persist for days or weeks, leading to recurring auroral displays that follow the solar wind structure. When Earth encounters long-duration solar wind streams with favorable magnetic field orientations, the aurora can remain active for extended periods, creating displays that evolve slowly over time scales of days. From space, these long-duration events appear as persistent auroral activity that waxes and wanes with the changing solar wind conditions. The aurora's influence on atmospheric dynamics creates effects that propagate downward through the atmosphere, potentially influencing weather patterns in the troposphere, where most weather phenomena occur. These atmosphere coupling effects represent one of the ways that space weather can influence terrestrial weather, creating connections between solar variability and Earth's climate system. From the International Space Station, these coupling effects are not directly visible, but represent an important aspect of the aurora's broader influence on Earth's environment. The aurora serves as a natural laboratory for studying fundamental plasma physics processes that occur throughout the universe. The same particle acceleration and wave-particle interaction processes that create the aurora also occur in planetary magnetospheres throughout the solar system and in astrophysical environments, ranging from stellar corona to galactic magnetic fields. From orbit, astronauts witness these universal physical processes in action, observing phenomena that help scientists understand plasma physics on scales ranging from planetary to cosmic. As we drift through this luminous realm high above our world, the aurora reveals itself as far more than a simple light show. It becomes a window into the fundamental forces that govern the relationship between stars and planets, a visible manifestation of the invisible connections that link our small world to the vast energies flowing throughout the cosmos. The dancing lights serve as a reminder that Earth exists not in isolation, but as part of a dynamic and interconnected system that extends from our planet's core to the farthest reaches of the solar system and beyond. The aurora's connection to Earth's deep interior reveals itself through subtle variations in magnetic field strength that create persistent patterns in the light displays. Regions where iron-rich rocks lie buried beneath the surface can influence the local magnetic field, creating auroral hotspots that appear night after night in the same locations. From the International Space Station, these geological influences become apparent as recurring bright spots that persist across multiple geomagnetic events, linking the dancing lights above to the ancient processes that shaped our planet's interior billions of years ago. The interaction between solar wind turbulence and Earth's magnetic field creates fractal patterns in the aurora that repeat at multiple scales. What appears as a smooth curtain of light from a distance reveals itself as a complex hierarchy of structures when observed more closely from orbit. Large-scale arcs contain smaller ripples, which in turn contain even finer details, creating a self-similar pattern that extends across spatial scales from kilometers to thousands of kilometers. This fractal nature reflects the turbulent processes in both the solar wind and Earth's magnetosphere, revealing the chaotic beauty of plasma physics in action. The aurora's response to Earth's magnetic field reversals, which occur irregularly over geological timescales, would create fundamentally different displays than those we observe today. During periods when Earth's magnetic poles swap positions, the aurora would undergo dramatic changes in location and intensity as the magnetic field weakens and reorganizes. From space, these transitional periods would reveal the aurora's complete dependence on magnetic field geometry, showing how even the most fundamental characteristics of our planet can reshape this celestial light show. The temperature structure of Earth's upper atmosphere creates invisible boundaries that influence where different types of auroral emissions can occur. Cold regions of the atmosphere favor certain chemical reactions, while warmer areas promote others, creating a complex three-dimensional chemical landscape that shapes the colors and intensities of auroral displays. From orbit, these temperature effects appear as subtle but systematic variations in auroral characteristics that change with altitude, latitude, and season. The aurora's interaction with atmospheric gravity waves creates rippling patterns that propagate across hundreds of kilometers of sky. These waves, generated by atmospheric turbulence or topographic features far below, modulate the density of gases at auroral altitudes in ways that create regularly spaced brightness variations. From the International Space Station, these wave-induced patterns appear as parallel bands of light and shadow that march slowly across the auroral display like the shadows of clouds moving across a landscape. The connection between the aurora and Earth's water cycle becomes apparent during certain atmospheric conditions, when water vapor at high altitudes influences the efficiency of auroral processes. Ice crystals formed in the upper atmosphere can affect particle precipitation patterns, creating subtle variations in auroral intensity that correlate with atmospheric humidity conditions. From space, these water-related effects appear as gradual changes in auroral brightness that reflect the complex interactions between space weather and Earth's atmospheric water content. The aurora's electromagnetic signature creates standing wave patterns in Earth's magnetosphere that can be detected as regular oscillations in the light display. These magnetospheric resonances act like organ pipes with different magnetic field line configurations, supporting different frequencies of oscillation. From orbit, these resonant modes appear as rhythmic pulsations in the aurora that can persist for hours, creating a visual representation of the natural frequencies of Earth's magnetic field system. The interaction between cosmic rays and Earth's atmosphere during auroral displays creates secondary particle showers that add to the complexity of the precipitation processes. High-energy cosmic ray particles, arriving from deep space, collide with atmospheric atoms to create cascades of secondary particles that can contribute to auroral emissions. From the International Space Station, these cosmic ray effects are generally invisible, but represent an additional source of atmospheric ionization that influences the background conditions for auroral displays. The aurora's role in atmospheric mixing creates vertical transport processes that move trace gases between different atmospheric layers. During intense displays, the energy deposition from auroral particles can drive convective motions that carry gases upward or downward through the atmosphere. From orbit, these mixing effects are not directly visible, but contribute to the complex atmospheric chemistry that influences everything from ozone concentrations to greenhouse gas distributions. The seasonal variations in Earth's orbital distance from the Sun create subtle but measurable effects on auroral intensity through their influence on the solar wind density at Earth's location. When Earth is closer to the Sun during its elliptical orbit, the slightly higher solar wind density can enhance auroral activity compared to periods when our planet is farther away. From space, these orbital effects appear as very gradual changes in average auroral brightness that cycle with Earth's yearly journey around the Sun. The aurora's interaction with the solar wind's magnetic field creates bow wave structures that propagate through Earth's magnetosphere like ripples on a pond. These magnetospheric waves can be observed from orbit as coordinated changes in auroral activity that sweep across the polar regions at predictable speeds. The wavefronts appear as bands of brightening that move through the auroral display, marking the passage of disturbances that originated millions of kilometers away in interplanetary space. The connection between the aurora and Earth's atmospheric escape processes reveals itself during periods of extreme geomagnetic activity when the energy input becomes so intense that atmospheric gases are heated to escape velocities. From the International Space Station, these escape events appear as faint upward streaming features that extend beyond the normal auroral altitudes, marking regions where Earth's atmosphere is literally boiling away into space under the influence of solar wind energy. The aurora's three-dimensional current systems create magnetic field configurations that can trap and accelerate particles to very high energies. These natural particle accelerators operate continuously in the auroral regions, creating populations of energetic electrons and ions that can pose hazards to spacecraft and astronauts. From orbit, these acceleration regions appear as particularly bright and active areas of the aurora, where particle energies reach their maximum values. The interaction between the aurora and Earth's neutral winds creates feedback effects that can modify the very atmospheric conditions that support auroral displays. Strong auroral heating can drive horizontal winds that transport atmospheric gases away from the auroral zone, changing the local atmospheric composition in ways that affect subsequent auroral activity. From space, these wind-driven effects appear as gradual changes in auroral morphology that reflect the evolving atmospheric conditions below. The aurora's response to variations in Earth's rotation rate, which changes slightly due to atmospheric and oceanic effects, creates subtle long-term variations in the timing and intensity of auroral displays. These rotational effects, though tiny, influence the coupling between Earth's magnetic field and the solar wind in ways that can be detected in long-term auroral statistics. From the International Space Station, these effects are far too small to observe directly, but represent one of the many ways that Earth's internal dynamics influence its space environment. The electromagnetic environment, created by auroral processes, generates radio noise that can interfere with sensitive scientific instruments throughout near-Earth space. This auroral radio interference can affect everything from astronomical observations to satellite communications, creating a complex electromagnetic environment that extends far beyond the visible auroral displays. From orbit, this radio environment is invisible to human senses, but represents an important aspect of the space weather conditions that affect technological systems. The aurora's interaction with Earth's plasmasphere boundary creates sharp transitions in the characteristics of the light display that mark the interface between different regions of the magnetosphere. These boundary effects appear from space as distinct edges or discontinuities in the aurora that remain relatively stable even as the overall display evolves. The boundaries serve as natural markers of magnetospheric structure, revealing the invisible architecture of Earth's magnetic environment. The connection between the aurora and solar wind pressure variations creates breathing modes in Earth's magnetosphere that cause the auroral oval to expand and contract rhythmically. These pressure-driven oscillations can cause the aurora to pulse with periods ranging from minutes to hours, creating displays that seem to breathe with the rhythm of solar wind variations. From the International Space Station, these breathing patterns appear as coordinated changes in auroral size and intensity that reflect the dynamic balance between solar wind pressure and magnetic field tension. The aurora's role in energy dissipation makes it a crucial component of the global energy balance during magnetic storms. The light displays represent the visible signature of enormous amounts of energy being transferred from the solar wind to Earth's upper atmosphere, where it is ultimately radiated away as heat. From orbit, this energy dissipation process appears as the brilliant auroral displays that can release energy equivalent to millions of lightning bolts simultaneously. The interaction between the aurora and Earth's ionosphere creates complex feedback loops that influence radio wave propagation throughout the polar regions. Changes in ionospheric density caused by auroral particle precipitation can affect radio communications over vast areas, creating blackout regions that move with the aurora itself. From space, these ionospheric effects are invisible to direct observation, but create measurable changes in the radio environment that can be detected by sensitive instruments. The aurora's connection to the interplanetary magnetic field polarity creates systematic differences between displays occurring during different magnetic field orientations. When the interplanetary field points northward, the aurora tends to be weaker and more confined to high latitudes, while southward fields create more intense and extensive displays. From the International Space Station, these polarity effects appear as fundamental changes in auroral character that can persist for days as Earth moves through different regions of the solar wind. The seasonal variations in atmospheric density at auroral altitudes create systematic changes in the altitude distribution of different auroral colors. During winter, When the upper atmosphere contracts due to reduced solar heating, red oxygen emissions tend to occur at lower altitudes relative to green emissions. From orbit, these seasonal color changes appear as gradual shifts in the vertical structure of the aurora that reflect the changing thermal state of the upper atmosphere. The aurora's electromagnetic waves can couple to Earth's surface through complex propagation mechanisms that allow space weather effects to influence ground-based technological systems. These coupling processes can induce electrical currents in power lines and pipelines, creating geomagnetically induced currents that can damage infrastructure thousands of kilometers away from the auroral displays themselves. From space, these coupling effects are invisible but represent an important way that auroral processes can influence human technology and society. The interaction between the aurora and Earth's magnetic field cusp regions creates unique particle precipitation patterns that produce distinctively different auroral morphologies. The magnetic cusps, where Earth's field lines connect directly to interplanetary space, allow solar wind particles to penetrate much deeper into the magnetosphere than elsewhere. From orbit, these cusp auroras appear as distinct features with characteristics that differ markedly from the more familiar oval-shaped displays at higher latitudes. The aurora's response to solar wind dynamic pressure changes creates sudden expansions and contractions of the auroral oval that can occur within minutes of pressure variations in interplanetary space. These pressure pulse effects propagate through Earth's magnetosphere at speeds much faster than the solar wind itself, creating nearly instantaneous responses in the auroral display to distant solar wind changes. From the International Space Station, these rapid responses appear as sudden brightenings or movements in the aurora that seem to anticipate changes in solar wind conditions. The connection between the aurora and Earth's ring current system creates complex interactions during the main phase of magnetic storms, when energetic particles become trapped in stable orbits around the planet. These trapped particles modify Earth's magnetic field in ways that affect auroral particle precipitation patterns, creating systematic changes in auroral morphology as storms develop and decay. From space, these ring current effects appear as gradual changes in auroral intensity and location that correlate with the overall magnetic storm evolution. The aurora's three-dimensional structure creates optical depth effects that influence the apparent brightness and color of the display depending on the viewing angle. Features that appear bright when viewed from one direction may appear dim when seen from another angle, creating perspective-dependent variations that are only apparent from the mobile platform of an orbiting spacecraft. From the International Space Station, these viewing angle effects become apparent as the aurora's appearance changes throughout each orbital pass. The electromagnetic turbulence associated with auroral displays creates a complex spectrum of wave modes that can accelerate particles to relativistic energies within Earth's magnetosphere. These wave-particle interactions represent some of the most efficient natural particle acceleration processes known, creating energetic electron populations that can persist for days or weeks after the auroral display itself has faded. From orbit, these acceleration processes are invisible to direct observation, but create measurable changes in the radiation environment throughout near-Earth space. The aurora's interaction with atmospheric tidal motions creates regular variations in display characteristics that follow the complex periodicities of atmospheric tides driven by solar heating and gravitational forces. These tidal effects can modulate auroral intensity and morphology with periods ranging from hours to days, creating predictable patterns that reflect the coupling between space weather and atmospheric dynamics. From the International Space Station, these tidal modulations appear as systematic variations in auroral activity that correlate with atmospheric tidal predictions. The connection between the aurora and Earth's thermosphere temperature creates feedback mechanisms that can amplify or dampen auroral activity depending on atmospheric conditions. Auroral heating increases thermosphere temperature, which can affect subsequent particle precipitation efficiency in ways that either enhance or suppress continued auroral activity. From space, these thermal feedback effects appear as changes in auroral persistence and intensity that reflect the evolving thermal state of the upper atmosphere. The aurora's role as a natural plasma laboratory provides insights into fundamental physical processes that occur throughout the universe in environments ranging from stellar atmospheres to galactic magnetic fields. The same wave-particle interactions and magnetic reconnection processes that create Earth's aurora also operate in these distant astrophysical environments, making auroral observations relevant to understanding cosmic phenomena on scales vastly larger than our planetary system. From orbit, astronauts witness these universal physical processes in action, observing laboratory-scale examples of physics that governs the behavior of matter throughout the cosmos. As we continue our silent journey through this realm of dancing light, the aurora reveals itself as a gateway to understanding the fundamental connections between our small world and the vast energies that flow through space. Each flickering curtain of light represents a moment when the invisible forces of the cosmos become visible to human eyes, transforming abstract physics into tangible beauty that can touch the soul as deeply as it illuminates the mind. The aurora stands as a reminder that we live not on an isolated world, but as part of an interconnected cosmic system where the breath of distant stars shapes the very air we breathe and the light that dances in our skies. System, where the breath of distant stars shapes the very air we breathe and the light that dances in our skies. In our skies, the aurora's relationship with Earth's bow shockwave creates compression effects that can be observed from orbit as sudden intensifications of the light display when solar wind pressure fronts arrive at our planet's magnetic boundary. These compression events propagate through the magnetosphere like ripples spreading across a pond, causing the entire auroral oval to brighten simultaneously across thousands of kilometers. From the International Space Station, these pressure-driven enhancements appear as coordinated flashes that illuminate the polar regions in perfect synchrony, demonstrating the global-scale organization of Earth's magnetic response to solar wind variations. The interaction between the aurora and Earth's neutral atmospheric winds creates a complex feedback system where auroral heating drives atmospheric circulation patterns that can modify the very conditions supporting the light display. During intense auroral events, the massive energy input heats the upper atmosphere so dramatically that it expands upward and flows horizontally away from the auroral zone, carrying atmospheric gases toward lower latitudes where they can affect the chemical composition of regions far removed from the original display. From space, these wind-driven effects appear as gradual changes in auroral morphology that reflect the evolving atmospheric conditions created by the aurora's own energy input. The aurora's connection to variations in Earth's magnetic dipole moment, which changes slowly over geological timescales, would fundamentally alter the characteristics of the light displays over periods of thousands or millions of years. As Earth's magnetic field strength waxes and wanes through natural cycles, the aurora would migrate to different latitudes and take on entirely different morphological characteristics. From orbit, these extremely long-term variations are impossible to observe directly, but they represent one of the ways that Earth's internal dynamics continue to shape the space environment over timescales that dwarf human civilization. The electromagnetic waves generated by auroral particle acceleration create resonant cavities within Earth's magnetosphere that can trap and amplify certain wave modes for extended periods. These trapped waves can persist long after the original auroral display has faded, continuing to accelerate particles and maintain populations of energetic electrons in regions far removed from the auroral zone itself. From the International Space Station, these wave-trapping effects are invisible to direct observation, but create measurable changes in the radiation environment that can affect spacecraft operations and astronaut safety for days after major auroral events. The aurora's interaction with the solar wind's velocity structure creates systematic patterns in display characteristics that reflect the large-scale organization of the solar wind as it streams away from the sun. Fast solar wind streams, typically originating from coronal holes, create auroral displays with distinctive, smooth-flowing characteristics, while slower, more turbulent solar wind produces more chaotic and rapidly changing light patterns. From space, these velocity-related effects appear as fundamental differences in auroral behavior that can persist for days as Earth moves through different solar wind regimes. The connection between the aurora and Earth's plasmasphere dynamics creates boundary phenomena that appear as sharp transitions in auroral characteristics, marking the interface between cold, dense plasma near Earth and the hot, tenuous plasma of the outer magnetosphere. These plasma boundaries can move inward and outward in response to geomagnetic activity, creating corresponding changes in auroral morphology as different particle populations gain access to the upper atmosphere. From orbit, these boundary effects appear as moving edges in the auroral display that track the dynamic evolution of plasma populations throughout Earth's magnetic environment. The aurora's role in driving atmospheric escape processes becomes particularly significant during periods of extreme geomagnetic activity, when the energy input from space becomes so intense that it can actually strip away portions of Earth's upper atmosphere. These escape events, though rare, represent moments when space weather directly influences the long-term evolution of our planet's atmospheric composition. From the International Space Station, these escape processes appear as faint upward streaming features that mark regions where atmospheric gases are being accelerated to velocities sufficient to overcome Earth's gravitational hold. The interaction between the aurora and Earth's radiation belt populations creates complex particle exchange processes that can rapidly transport energetic electrons and ions between different regions of the magnetosphere. During magnetic storms, particles can be transferred from the stable radiation belt orbits into the loss cone, where they precipitate into the atmosphere to create auroral displays, while other particles are simultaneously accelerated and trapped to replenish the radiation belt populations. From space, these particle exchange processes appear as changes in auroral intensity and morphology that correlate with radiation belt dynamics throughout the magnetosphere. The aurora's response to the tilt angle of Earth's magnetic dipole relative to the planet's rotation axis creates systematic variations in display characteristics that change with magnetic local time as the dipole rotates through different orientations relative to the solar wind flow. These dipole tilt effects cause the aurora to appear brighter and more active on one side of the magnetic pole compared to the other, creating asymmetries that shift systematically as Earth rotates. From orbit, these tilt-related asymmetries appear as persistent brightness variations that rotate around the magnetic poles with Earth's 24-hour period. The connection between the aurora and atmospheric gravity wave propagation creates modulation effects, where waves generated by atmospheric turbulence or topographic features far below can influence the density structure of gases at auroral altitudes. These gravity wave effects create regularly spaced variations in atmospheric density that modulate auroral emission intensity, producing banded or striped patterns that march slowly across the display. From the International Space Station, these wave-induced patterns appear as parallel bands of enhanced and diminished auroral brightness that propagate across hundreds of kilometers of sky. The aurora's interaction with Earth's ionospheric irregularities creates scintillation effects in radio signals passing through the auroral region, causing rapid fluctuations in signal strength that can severely disrupt satellite communications and navigation systems. These scintillation effects extend far beyond the visible auroral boundaries, creating communication blackout zones that can cover areas larger than entire continents. From space, these ionospheric disturbances are invisible to direct observation, but create measurable changes in radio wave propagation that affect technological systems throughout the polar regions. The seasonal variations in the height of Earth's atmosphere create systematic changes in the altitude distribution of auroral emissions as the thermosphere expands and contracts in response to changing solar heating. During solar maximum periods, when increased solar radiation heats and expands the upper atmosphere, auroral emissions tend to occur at higher altitudes, where the expanded atmosphere provides different interaction conditions for precipitating particles. From orbit, these seasonal atmospheric effects appear as gradual changes in the vertical structure of the aurora that reflect the thermal state of the upper atmosphere. The aurora's electromagnetic signature creates induced current systems in Earth's conducting interior that generate secondary magnetic fields opposing the changes in the external field. These induced currents, flowing deep within Earth's mantle and core, create magnetic field perturbations that can be detected at Earth's surface and influence the morphology of auroral displays occurring thousands of kilometers above. From the International Space Station, these deep Earth effects are invisible but represent one of the ways that auroral processes create connections between the space environment and our planet's deep interior. The interaction between the aurora and solar wind magnetic field fluctuations creates wave modes that can propagate both parallel and perpendicular to Earth's magnetic field lines, generating complex interference patterns in the particle precipitation processes. These wave interference effects can create regularly spaced auroral arcs or produce more chaotic precipitation patterns, depending on the relative phases and amplitudes of the interfering waves. From space, these wave-related patterns appear as systematic structures in the aurora that reflect the wave physics occurring throughout the magnetosphere. The aurora's connection to Earth's magnetic field line resonance frequencies creates harmonic oscillations that can be observed as regular pulsations in the light display, with periods determined by the length and tension of individual field lines. Different field lines support different resonant frequencies, creating a complex spectrum of oscillation modes that give the aurora its characteristic rhythmic behavior. From orbit, these resonant oscillations appear as coordinated pulsations that can span entire field line systems, revealing the musical properties of Earth's magnetic field configuration. The interaction between cosmic ray particles and Earth's atmosphere during auroral displays creates additional ionization sources that can influence the background conditions for auroral processes. High-energy cosmic rays, arriving from galactic sources, create cascade showers of secondary particles when they collide with atmospheric atoms, adding to the complex particle environment in which auroral processes occur. From the International Space Station, these cosmic ray effects are generally too subtle to observe directly, but represent an additional source of atmospheric ionization that contributes to the overall space weather environment. The aurora's role in coupling energy between different regions of Earth's magnetosphere creates global circulation patterns where energy deposited in one region can influence conditions throughout the entire magnetic environment. These energy circulation effects can cause auroral activity in one hemisphere to influence displays in the opposite hemisphere, creating interhemispheric conjugacy effects that demonstrate the global nature of magnetospheric processes. From space, these coupling effects appear as correlated changes in auroral activity that span both hemispheres simultaneously. The connection between the aurora and Earth's neutral atmospheric composition creates chemical reaction pathways that can produce trace gases with atmospheric lifetimes ranging from minutes to months. These auroral chemistry effects can influence atmospheric composition over large regions, creating changes in minor atmospheric constituents that persist long after the visual display has faded. From orbit, these chemical effects are invisible to direct observation, but create measurable changes in atmospheric properties that can affect everything from radio propagation to atmospheric chemistry models. The aurora's interaction with magnetospheric substorms creates explosive releases of stored magnetic energy that can illuminate entire continents within minutes. These substorm events begin with energy storage in Earth's magnetic tail during periods of southward interplanetary magnetic field, followed by sudden energy release that creates dramatic auroral expansions and intensifications. From the International Space Station, these substorm sequences unfold like slow-motion explosions of light that can transform quiet auroral arcs into brilliant displays covering thousands of square kilometers. The electromagnetic turbulence associated with auroral regions creates a complex spectrum of plasma waves that can scatter and accelerate particles throughout a broad range of energies. This wave-particle interaction processes represent some of the most efficient natural particle acceleration mechanisms known, capable of accelerating electrons from thermal energies to relativistic speeds within seconds. From space, these acceleration regions appear as particularly active and bright portions of the aurora, where particle energies reach their maximum values. The aurora's response to variations in solar wind ram pressure creates breathing modes in the magnetosphere, where the entire auroral oval expands and contracts in response to pressure changes in the solar wind. These pressure-driven oscillations can cause systematic variations in auroral morphology, with periods ranging from minutes to hours, reflecting the dynamic balance between solar wind pressure and magnetic field tension. From orbit, these breathing patterns appear as coordinated size changes in the auroral oval that track solar wind pressure variations with remarkable fidelity. The interaction between the aurora and Earth's magnetic field cusp regions creates particle precipitation patterns with characteristics that differ markedly from those occurring in the main auroral oval. The magnetic cusps, where field lines connect directly to interplanetary space, allow direct access for solar wind particles to precipitate deep into the magnetosphere, creating auroral forms with unique morphological and temporal characteristics. From the International Space Station, these cusp auroras appear as distinct features that often show more direct correlation with solar wind conditions than the more familiar oval auroras at higher magnetic latitudes. The aurora's connection to magnetic field line merging processes creates transient brightening events that can propagate along auroral arcs at speeds of several kilometers per second. These traveling auroral features reflect the propagation of magnetic reconnection effects through the magnetosphere, carrying information about reconnection sites located thousands of kilometers away in space. From space, these propagating brightenings appear as waves of enhanced auroral intensity that sweep along existing auroral structures, revealing the connectivity between distant magnetospheric regions. The seasonal variations in Earth's heliospheric position create subtle but measurable effects on auroral activity through changes in the solar wind conditions encountered by our planet as it orbits the Sun. When Earth is upstream in the solar wind flow relative to its orbital motion, slightly different solar wind conditions are encountered compared to periods when the planet is downstream. From orbit, these heliospheric position effects appear as very gradual seasonal modulations in average auroral activity levels that reflect Earth's changing relationship to the solar wind flow. The aurora's interaction with Earth's atmospheric tidal systems creates regular modulations in display characteristics that follow the complex periodicities of atmospheric motions driven by solar heating and lunar gravitational forces. These tidal effects can influence auroral morphology through changes in upper atmospheric density and neutral wind patterns that affect particle precipitation efficiency. From the International Space Station, these tidal modulations appear as systematic variations in auroral intensity and structure that correlate with atmospheric tidal predictions. The connection between the aurora and magnetospheric convection patterns creates systematic flow patterns in the auroral display that reflect the large-scale circulation of plasma throughout Earth's magnetic environment. These convection-related motions appear as organized drifts and flows in auroral structures that can persist for hours during steady solar wind conditions. From space, these convection signatures appear as systematic motion patterns in the aurora that reveal the invisible circulation of charged particles throughout the magnetosphere. The aurora's electromagnetic environment creates natural radio transmitters that generate signals spanning a broad frequency range from extremely low frequencies to optical wavelengths and beyond. This electromagnetic spectrum provides information about different physical processes occurring in the auroral region, from large-scale current systems to microscale particle acceleration mechanisms. From orbit, sensitive instruments can detect portions of this electromagnetic signature, providing a multispectral view of auroral processes that complements visual observations. The interaction between the aurora and Earth's thermospheric winds creates feedback mechanisms where auroral heating drives atmospheric circulation that can modify the neutral atmospheric conditions affecting subsequent auroral development. Strong auroral heating can generate horizontal winds exceeding several hundred meters per second, transporting atmospheric constituents over large distances and altering the chemical composition of regions far from the original auroral zone. From the International Space Station, these wind-driven effects appear as gradual evolution in auroral characteristics that reflect the changing neutral atmospheric environment. The aurora's role in the global electrical circuit connects auroral current systems to electrical phenomena occurring throughout Earth's atmosphere, from the ionosphere down to the surface, where lightning and other electrical activities complete global current loops. These connections mean that auroral activity can influence electrical conditions throughout the atmosphere, affecting phenomena as diverse as lightning frequency and atmospheric electrical field variations. From space, these global electrical connections are invisible but represent an important aspect of how auroral processes influence Earth's entire atmospheric electrical environment. The connection between the aurora and interplanetary shockwaves creates sudden commencement effects, where the arrival of solar wind disturbances can trigger nearly instantaneous responses in auroral activity worldwide. These shock-related effects propagate through the magnetosphere much faster than the solar wind itself, creating coordinated auroral responses that can occur within minutes of shock arrival at Earth's bow shock. From orbit, these sudden commencement events appear as synchronized brightenings of the aurora that demonstrate the rapid communication of information throughout Earth's magnetic environment. The aurora's interaction with Earth's plasmasphere boundary layer creates particle populations with unique characteristics that contribute distinctively to auroral displays during different phases of geomagnetic activity. The plasmasphere boundary represents a sharp transition in plasma density and composition that can trap and modify particle populations before they precipitate to create auroral emissions. From the International Space Station, these boundary-related effects appear as systematic variations in auroral morphology that correlate with plasmasphere dynamics throughout geomagnetic storm cycles. As we continue our gentle drift through this luminous theater high above our world, the aurora reveals new layers of complexity with each passing moment. The dancing lights begin to seem less like a simple atmospheric phenomenon and more like a vast symphony of interconnected processes that link our planet to the farthest reaches of space. Each shimmering curtain represents a moment when invisible cosmic forces become visible to human eyes, transforming the abstract mathematics of plasma physics into tangible beauty that speaks directly to the soul. From this orbital perspective, we begin to understand that the aurora serves as more than just a spectacular light show. It becomes a visible manifestation of the dynamic relationship between Earth and Sun, a constantly changing display that reflects the ebb and flow of solar activity and the complex response of our planet's magnetic environment. The lights dance not randomly, but in patterns determined by physical laws that govern the behavior of matter and energy throughout the universe. The silence of space adds a profound dimension to this experience that ground-based observers can never fully appreciate. In the vacuum surrounding the International Space Station, the aurora unfolds in perfect quiet, its motions seeming even more graceful and mysterious without any accompanying sound. This silence allows the observer to focus entirely on the visual spectacle, to become completely absorbed in the flowing patterns of light without any distractions from the terrestrial world far below. The three-dimensional perspective available from orbit reveals the aurora as a truly sculptural phenomenon, with depth and volume that ground-based observations can only hint at. The lights appear to have substance and texture, like luminous fog banks suspended in the thin upper atmosphere, their forms shifting and evolving with each passing moment as new particles arrive from space and atmospheric conditions change in response to the continuing energy input. The colors of the aurora, so vivid and varied when seen from space, tell stories written in the fundamental language of atomic physics. Each hue represents a specific atomic transition, a moment when an atom absorbs energy from a collision with a charged particle and then releases that energy as a photon of light. The resulting palette spans the visible spectrum and beyond, creating combinations that no human artist could imagine and no earthly pigment could reproduce. The scale of the phenomenon becomes truly apparent only from this orbital vantage point. What appears from the ground as an overhead canopy reveals itself from space as a planetary scale process that can span entire continents and reach from the upper atmosphere deep into space. The aurora connects the solid Earth below to the cosmic environment above, serving as a bridge between the terrestrial and the celestial, the familiar and the infinite. The aurora's constant change and evolution reflect the dynamic nature of the space environment in which Earth exists. Nothing in this display is static or permanent. Every pattern, every color, every motion responds to conditions that are themselves constantly changing as the solar wind varies, as Earth rotates through different orientations, and as the complex interplay of magnetic and electric fields creates new configurations and possibilities for particle interaction. The beauty we witness from this orbital perspective represents just a tiny fraction of the energy and matter flowing through the space around our planet. The visible aurora is merely the observable signature of processes involving particle fluxes, magnetic field variations, and electromagnetic waves that extend throughout the entire magnetosphere and beyond. We see only what our eyes can detect, but the full phenomenon encompasses energies and scales that dwarf human comprehension. Yet in this vastness, there remains something deeply intimate about the aurora. Each photon of light represents an individual atomic interaction, a single moment when a particle from the sun meets an atom of Earth's atmosphere and creates a brief flash of illumination. The grand displays we observe from space are composed of billions upon billions of these microscopic events, each one a tiny bridge between the cosmic and the atomic, the vast and the infinitesimal. The aurora serves as a reminder that Earth is not an isolated world, but a dynamic participant in the solar system's complex web of interactions. The same solar wind that creates our auroral displays also shapes the magnetic environments of other planets, creating similar phenomena throughout the solar system. We are witnessing not just a terrestrial event, but a universal process that occurs wherever magnetic fields and charged particle streams interact in the cosmic environment. The aurora's connection to Earth's internal magnetic dynamo reveals itself through subtle variations that reflect the slow changes occurring deep within our planet's core. The molten iron that generates Earth's magnetic field moves in complex patterns driven by heat flow and planetary rotation, creating variations in field strength that can influence auroral displays over timescales ranging from years to decades. From the International Space Station, these deep Earth effects appear as gradual long-term changes in auroral morphology that track the evolution of our planet's magnetic field configuration. The interaction between the aurora and atmospheric molecular oxygen creates distinctive red emissions that become particularly prominent during periods of high solar activity, when particle precipitation extends to higher altitudes. These red oxygen emissions occur at altitudes above 300 kilometers, where the thinner atmosphere allows excited oxygen atoms more time to radiate their stored energy before colliding with other particles. From orbit, these high-altitude red emissions appear as a luminous crown extending upward from the more familiar green curtains below, creating a layered display that reveals the vertical structure of particle precipitation processes. The aurora's response to Earth's seasonal atmospheric bulge creates systematic variations in display characteristics as our planet's upper atmosphere expands and contracts in response to changing solar heating throughout the year. During summer months, the heated atmosphere extends higher into space, providing different interaction conditions for auroral particles compared to the contracted winter atmosphere. From space, these seasonal atmospheric effects appear as gradual changes in the altitude distribution of auroral colors and intensities that follow predictable annual patterns. The connection between the aurora and magnetospheric magnetic field lines stretching creates dynamic displays during periods when Earth's magnetic tail becomes highly elongated by solar wind pressure. These field line stretching effects can store enormous amounts of magnetic energy that is later released explosively during substorm events, creating some of the most dramatic auroral displays visible from space. From orbit, these energy storage and release cycles appear as periods of quiet, followed by sudden brilliant expansions that can illuminate entire hemispheres within minutes. The aurora's electromagnetic environment generates radio waves that can propagate around Earth's magnetic field lines, creating natural radio phenomena that can be detected thousands of kilometers away from the original auroral source. These auroral radio emissions carry information about particle acceleration processes occurring in the auroral region, providing remote sensing capabilities for understanding auroral physics. From the International Space Station, these radio emissions are invisible to human senses, but create a complex electromagnetic environment that sensitive instruments can detect and analyze. The interaction between the aurora and Earth's neutral atmospheric chemistry creates cascade reactions that can produce trace atmospheric constituents with lifetimes extending far beyond the duration of the original light display. These chemical products can influence atmospheric composition over large regions, affecting everything from ozone concentrations to the efficiency of radio wave propagation through the ionosphere. From space, these chemical effects are invisible, but represent an important way that brief auroral displays can have lasting impacts on atmospheric properties. The aurora's connection to solar wind magnetic field rotation creates spiral patterns in particle precipitation that reflect the twisted structure of interplanetary magnetic fields as they are carried outward by the expanding solar wind. These magnetic field spirals, created by the sun's rotation, can create corresponding spiral patterns in auroral displays when conditions are favorable for direct magnetic field line connection between Earth and interplanetary space. From orbit, these spiral auroral features appear as graceful curved structures that seem to rotate slowly across the polar landscape. The seasonal variations in Earth's magnetic field orientation, relative to the ecliptic plane, create systematic changes in the efficiency of solar wind coupling that influence auroral activity levels throughout the year. During equinoctial periods, when Earth's magnetic dipole is optimally oriented relative to typical interplanetary magnetic field directions, auroral activity tends to reach seasonal maxima. From the International Space Station, these seasonal coupling effects appear as predictable variations in average auroral intensity that correlate with Earth's orbital position and magnetic field geometry. The aurora's interaction with magnetospheric particle drift motions creates systematic flow patterns that can be observed as organized motion within auroral structures. Charged particles trapped in Earth's magnetic field undergo complex drift motions that depend on their energy and the local magnetic field configuration, creating circulation patterns that influence where and how auroral precipitation occurs. From space, these particle drift effects appear as systematic flows and motions within the auroral display that reveal the invisible circulation of energetic particles throughout the magnetosphere. The connection between the aurora and Earth's bow-shock orientation creates variations in particle acceleration efficiency that depend on the angle between the shock normal and the interplanetary magnetic field direction. These shock geometry effects can create systematic differences in the energy spectrum of particles reaching the auroral zone, influencing both the intensity and color characteristics of the resulting light displays. From orbit, these shock-related effects appear as systematic variations in auroral morphology that correlate with the changing orientation of Earth's bow shock relative to the solar wind flow. The aurora's role in magnetospheric energy circulation creates global current systems that can influence magnetic field conditions throughout near-Earth space. These auroral current systems, carrying millions of amperes of electrical current, generate magnetic field perturbations that can be detected by spacecraft throughout the magnetosphere. From the International Space Station, these current-related magnetic field changes are invisible, but create measurable effects on the space environment that can influence everything from particle trajectories to radio wave propagation. The interaction between the aurora and Earth's plasmasphere refilling processes creates temporal variations in display characteristics that reflect the changing density structure of cold plasma populations near Earth. Following magnetic storms, the plasmasphere gradually refills with material from the ionosphere, creating evolving density gradients that influence auroral particle precipitation patterns. From space, these refilling effects appear as systematic changes in auroral morphology that evolve over timescales of days following major geomagnetic disturbances. The aurora's connection to interplanetary coronal mass ejection impacts creates some of the most spectacular displays visible from orbit when these massive solar wind disturbances engulf Earth's magnetosphere. The compressed magnetic fields and enhanced particle fluxes associated with coronal mass ejections can drive auroral activity to extraordinary levels, creating displays that can be seen from space stations, aircraft, and even from the ground at latitudes far from the normal auroral zones. From the International Space Station, these coronal mass ejection-driven displays appear as brilliant cascades of light that can persist for hours as the solar disturbance passes over Earth. The electromagnetic waves generated by auroral particle acceleration create resonant interactions with Earth's radiation belt populations, efficiently transferring energy between different particle populations throughout the magnetosphere. These wave-particle resonances can accelerate radiation belt electrons to relativistic energies, while simultaneously causing other particles to precipitate into the atmosphere to create auroral displays. From orbit, these resonant acceleration processes are invisible, but create correlated variations in both auroral activity and radiation belt intensity that reveal the coupled nature of magnetospheric particle populations. The aurora's interaction with atmospheric planetary waves creates modulation effects, where large-scale atmospheric motions can influence the neutral atmospheric conditions at auroral altitudes. These planetary wave effects, driven by atmospheric heating patterns and topographic features, can create systematic variations in atmospheric density and composition that affect auroral emission characteristics. From the International Space Station, these planetary wave influences appear as systematic patterns in auroral intensity and morphology that correlate with large-scale atmospheric circulation patterns. The connection between the aurora and Earth's magnetic field, secular variation creates long-term trends in auroral occurrence patterns that reflect the gradual evolution of our planet's internal magnetic field. The magnetic poles drift slowly across Earth's surface as the internal dynamo process evolves, causing corresponding shifts in the locations where auroral displays are most likely to occur. From space, these secular variation effects are too slow to observe directly, but represent important long-term changes in the geographic distribution of auroral activity. The aurora's response to solar wind temperature variations creates subtle but systematic differences in particle precipitation characteristics that influence both the intensity and spectral properties of the resulting light displays. Hotter solar wind tends to produce more energetic particle populations that can penetrate deeper into Earth's atmosphere, while cooler solar wind creates different precipitation patterns with distinct morphological signatures. From orbit, these temperature-related effects appear as systematic variations in auroral characteristics that correlate with solar wind thermal properties measured by upstream spacecraft. The interaction between the aurora and magnetospheric magnetic reconnection sites creates traveling features that propagate along auroral arcs at speeds determined by the alphen wave velocity in the local plasma environment. These traveling auroral disturbances carry information about reconnection processes occurring at distant locations in Earth's magnetosphere, providing remote sensing capabilities for understanding magnetic topology changes throughout the system. From the International Space Station, these propagating features appear as waves of enhanced auroral brightness that sweep along existing structures, revealing the connectivity between different magnetospheric regions. The aurora's connection to Earth's ionospheric plasma fountain creates coupling between auroral processes and equatorial plasma dynamics through field-aligned currents that flow between the auroral zones and the magnetic equator. These current systems can transport both energy and plasma between high-latitude auroral regions and the equatorial ionosphere, creating conjugate effects where auroral activity influences plasma conditions thousands of kilometers away. From space, these coupling effects are invisible but represent important connections between auroral processes and global ionospheric dynamics. The seasonal variations in cosmic ray intensity create systematic changes in atmospheric ionization rates that can influence the background conditions for auroral processes throughout the year. During periods of reduced cosmic ray intensity, typically associated with high solar activity, the background ionization of the upper atmosphere decreases, creating different conditions for auroral particle precipitation. From orbit, these cosmic ray-related effects are too subtle to observe directly, but contribute to the complex space weather environment that influences auroral development and evolution. The aurora's electromagnetic signature creates natural lightning rods in the upper atmosphere that can influence the global atmospheric electrical circuit by providing enhanced conductivity paths between the ionosphere and lower atmospheric regions. These auroral conductivity enhancements can affect electrical field distributions throughout the atmosphere, potentially influencing phenomena ranging from lightning frequency to atmospheric electrical field variations measured at Earth's surface. From the International Space Station, these global electrical effects are invisible, but represent an important way that auroral processes can influence Earth's entire atmospheric electrical environment. The interaction between the aurora and Earth's neutral atmospheric escape processes creates feedback mechanisms where auroral heating can enhance atmospheric loss rates during periods of intense geomagnetic activity. The energy deposited by auroral particles can heat atmospheric gases to temperatures sufficient to increase their scale heights and enhance escape rates, contributing to the long-term evolution of Earth's atmospheric composition. From space, these escape enhancement effects appear as subtle changes in atmospheric density profiles that correlate with auroral heating rates. As our gentle journey through this luminous realm draws to a quiet close, we drift back toward Earth, carrying with us the profound beauty of the aurora as seen from space. From this orbital perspective, we have witnessed not just a light show, but a cosmic conversation between sun and planet. A visual symphony that reveals the invisible forces connecting our world to the vast energies flowing throughout the universe. The dancing lights serve as a reminder that we live not in isolation, but as part of something infinitely larger and more wondrous than ourselves. Rest well, knowing that above us, this celestial ballet continues through the night, painting the darkness with colors that speak to the deepest mysteries of our cosmic home.